And welcome back. Well, we're talking about applications of all these things we've seen in this course. And now, okay, let's talk about another very well-known application, which is applications in medicine and health. Right? When we think nuclear, we usually think either of energy or of health. So, essentially, one of the most common ways of using nuclear technology in health is by producing radionuclides. I mean, for some way you want to produce nuclides that will emit radiation inside your body, either for diagnostic purposes or for treatment purposes, right? And how do we produce radionuclides? Well, if you listen carefully to all I've said so far, you already know this answer, right? We produce radionuclides by doing nuclear reactions, right? So, if we don't do nuclear reactions, we do not produce radionuclides, right? If we don't do nuclear reactions, the radiation will only interact with electrons, and electrons have nothing to do with the nucleus. You do chemical change, but no physical change. If you interact with the nucleus, meaning if you do have nuclear reactions, you will produce radionuclides, or can produce. And there's two ways of producing, essentially. If you want neutron-rich nuclei, you irradiate them with neutrons, right? And I said neutrons are very good for doing nuclear reactions because they do not have charge and everything. So usually, if you want a neutron-rich nucleus, you use a nuclear reactor, right? They can be alpha or beta emitters, usually alpha or beta minus emitter, most of them beta minus emitters. Beta minus, right, sorry. If you want proton-rich emitters, we want to put some more charge, and then putting more neutrons is not the answer. So what we can do particle accelerators, and a particle accelerator in this case is essentially an accelerator in which you accelerate a positive ion, maybe hydrogen, maybe helium, maybe carbon, whatever, and you cause a nuclear reaction, and this nuclear reaction will produce neutron poor, meaning proton-rich things, and proton-rich things tend to decay by beta plus, right? So you can produce beta minus emitters too through accelerators, right? It's also possible, and it's also done, but most of the research on accelerators tends to think of beta plus. So the first thing, if we want neutron-rich react products, we think of a nuclear reactor. The advantages of nuclear reactors are they are a very strong source. It's easy to get fluxes like 10 to the 12th or 10 to the 14th neutrons per square centimeter per second. It's a lot. The number may not mean much to you, but it's orders of magnitude, maybe 5 orders of magnitude more than you can get in an accelerator. So you can produce a lot of material. You can produce very, very radioactive material, right? So we usually produce neutron-rich products, right? Because we're adding neutrons to things. And as neutrons, they have, if you remember, I told you that neutrons interact in essence very weakly with matter. So your samples can be large because you will irradiate all of it at the same time. Even if it's a large sample, most of it will be mostly, the neutron flux will be mostly homogeneous, even in a large source, in a large sample. And targets are very easy to produce because there's you're not exposing anything to heat or anything. Just maybe you will put things underwater. That's possibly what happens. So you can obtain the target holders are simple, whatever you want, in fact. you can irradiate large masses. You can get very, very large activities because large masses and large flux. Cross sections are usually small, but not that small. So you mostly use isotopically enriched targets, but sometimes it's possible to work without them, right? But there's a trick here, because if I think I'm depositing a neutron here, so let's get an example. I have lutetium 176, and it's very good at absorbing neutrons. You produce lutetium 177. Now, how can I separate? After I have irradiated, I have a mix of both. How can I separate lutetium 176 from lutetium 177? Very, very hard to do, not to say it's impossible. In practical ways, it's impossible. So you will always have to, this is what we call carrier. The carrier is the original radionuclide. It's almost impossible to get rid of it. So you have to deal with the radionuclide, which is mixed with the stable nuclide, right? It may reduce in the end the overall dose you can implant in a patient. Essentially, so as I said, the main reaction is N-alpha, right? And the other problem, the carrier separation, can be challenging, to put it mildly, and radioactive waste management is required because things get too radioactive. Everything gets very radioactive in this case. And what we usually produce in nuclear reactions, all these isotopes here that will go from 6 days, from 2 days to, I don't know, 27 days or 70 days or something. The ones in black are the most important ones. Molybdenum 99, you produce it, it's the father, it's the parent of technetium-99 metastable, which is by far the most widely used radioisotope in nuclear medicine. Is used from cancer diagnosis to, it's only diagnostics, right? It doesn't do therapy, but it's used for brain diagnosis of brain function, of heart function, of cancer. So it's by far the most used one, right? You have molybdenum, which then decays in, it's essentially transient equilibrium. So molybdenum 99 produces technetium 99 metastable, and this is what we call a generator, right? You distribute molybdenum 99 and you just get technetium. You have several resin columns and you can separate them. Then you don't have carrier issues. These two are very used to, and these two we used to produce in EPEN. We are not producing now. These ones we wanted to produce, we can't. Efficiency in our reactor would be too low. If you've heard of a project called RMB, a Brazilian multi-purpose reactor, the idea is to have a reactor that's strong enough so that it can produce this. Argentina, close to us, Argentina produces it, South Africa produces it, Canada produces it, United States only produces for internal consumption. We usually, in Brazil, we have to import it from essentially Argentina, Canada, South Africa, or Russia, right? So what we used to produce here, not producing now just for political questions, we should be producing them again soon, hopefully, are iodine 131. You can just use it both for diagnosis and treatment of thyroid issues, right? You have samarium 153, which is used, this was what we produced most in recent years, used to reduce the pain associated with metastasis in bones, right? And in red here is is now the star of those two, all of those. Lutetium-177, I just talked about it a bit ago. It's used in clinical trials. As of now, it's in clinical trials. Has started to go clinical, really, in other countries, not in Brazil. And it can be used to, it's what they call, the name for this is theranostic nuclide, meaning it does therapy and diagnostics together. You can put it so that it will at the same time destroy the tumor and give you real-time imaging of where the dose is going. It's very promising, and we have studies here in our institute trying to produce here. It is possible to produce this in Brazil in our reactor as of now, right? And just to show, and this iridium-192, it's usually produced in the form of small wires or something, right? Then we go for the other side. We have the particle accelerators. Then we have beams of high energy charged particles and do nuclear reactors. This now has an issue of itself because you have very high energy and you stop it here, you produce a lot of heat. Now there's a problem because, first of all, if you remember, heavy charged particles have a very, very short range, right? Meaning, and then you see that all things we have learned so far start to come here. If the range is too short, the target must be thin. The other thing sometimes they do is use gas as a target, because then you can increase a bit the volume you can irradiate, right? So this is a big problem. And the second big problem, you produce a lot of heat because you're having very energetic particles here. It will produce a lot of kinetic recoil on the nuclei too, and recoil means movement, which means temperature. So we have to cool down the target. It's never really simple to do that, right? Because you don't want your cooler to somewhat interfere in the reaction itself or to become radioactive. It can be done. It's just quite complex. The cross sections are usually a lot lower, so targets essentially must be isotopically enriched, which make them a lot more expensive. And the way the target has to be thin. You have to think, if it can't be in normal atmosphere, it usually can't. The way you contain it is harder because the beam will hit the container too. So there's a lot of things that have to be think of. It's a more complex machine also, right? But you can do, and we do it a lot, usually use cyclotrons and produce a lot of, for instance, iodine-123. And mostly these products decay by electron capture or beta plus, but as I said, okay, there are things that decay by beta minus too. Okay, so cyclotrons are usually the answer because they are kind of accelerator where you can get higher intensity beams, on opposition to things that produce higher energy beams with low intensity. Here we want energies don't have to be that high, but we need a lot of energies must be on the MeV scale, several MeV, but not those much MeV, but you need a lot of current, right? So cyclotrons have the advantage that you can use several distinct energies or particles depending on what reaction you want to do. Remember that cross-section reactions, they vary very much with energy, so you have to choose well your energy to produce mostly the particle you want, right? And these are, for instance, some of the reactions we have on the cyclotron. It's not stopped. It's now stopped, but it used to work well here in our institute, producing fluorine 18 using essentially oxygen 18 as a target and doing a PN reaction. Right, you accelerate a proton, produce a neutron. And this is a photo of the small cyclotron, the one that was used essentially to produce fluorine-18. And this guy here, he's retired by now. His name was Valdir. He's a very nice guy, by the way. Okay, so what can we usually produce in cyclotrons? Well, there's these three here, these four here. They are mainly used for, I don't know if you ever heard of PET scans, right? Positron emission tomography. We'll talk about them in a few slides. But these are the most used ones in in positron emission tomography, right? In black we have fluorine-18, which we used to produce in EPEN, and there's also other things like copper-64 and these three here in black: gallium-67, iodine-123, and thallium-201. We used to produce in our institute as well. We're not producing them anymore, unfortunately. Once again, because of political questions, I don't want to go that way. But if we talk outside class, maybe we can discuss that if you're interested. But that's essentially the problem. Okay, so we can produce a lot of things that can be used to a lot of things too. Essentially, all of these are essentially for just diagnostic purposes, not for treatment purposes. And one thing we use a lot are generators, which mean, okay, let's use equilibrium to our favor. You produce the father, either in a reactor or in an accelerator, and then you just let it decay and keep on producing the shorter-lived daughter for a long time. I already talked about the most important and known one, which is molybdenum, because see, we do not produce molybdenum in Brazil. So how can we, if technetium has 6 hours half-life, how can we import this? It's impossible. We imported a lot of those from the Canada, and 12 hours flight, plus 6 hours to put this in a plane there, 6 hours to take it from a plane here and to take it somewhere. We're already talking 4 half-lives you lost, right? But no, we can import molybdenum, and just Moly-99 as they call. And Moly-99 will decay and produce technetium. It's a case of transient equilibrium. So if you remember, yes, you have the activity of technetium-99. It is produced the whole time with an activity. Once you reach equilibrium, the activity is slightly larger than the one you had from Moly. And they are also quite simple to separate chemically. So you have a pure source of technetium-99 metastable. Same goes for tin-113 decaying for it's more than 100 days, and you can produce this less than 2 hour thing, which is indium-113. Rubidium can produce kryptonium, which is a gas, and being a noble gas with a very short half-life, it has some interesting uses, but you have to, would be impractical to have handled something with a 13-second half-life, but you can just drain it. And being a gas, rubidium is not a gas, it just exhalates from the generator. There's germanium, gallium. This one we use a lot too, right, for other purposes, but we use a lot in Brazil also. And so what we do now, we know how to do radioisotopes, and there's not only radioisotopes. Maybe you've heard that some hospitals have accelerators. Some of these accelerators are for producing radioisotopes, then they are usually cyclotrons. But they also have other types of accelerators and other types of stuff, because sometimes we want to diagnose an illness, sometimes we want to treat an illness. And when we want to treat an illness, we call it radiotherapy, right? And radiotherapy means very high radiation doses. And then, of course, this would mean a lot of problems in the whole of your body, which unfortunately happens a bit if you've seen someone who has done radiotherapy. They have probably gone bald and had some issues with their health during the treatment, because it's hard to get all those only in the ideal world you have those only on your tumor, which is not the case, unfortunately. It's never the case. You can do it closer to ideal, doing various tricks. The idea is a very high radiation dose will mean that one thing I haven't told before, but usually the larger a molecule is, the more radiation sensitive it is, because it has more chemical binds. And what radiation does, when radiation, we say it ionizes things, it means if the atom is here by itself, you just ionize it. But if the atom is part of a molecule or something, you will eventually break down that molecule. And large molecules have many bindings, so many atoms, many bindings, they're easier to break. So the concept is, okay, let's break cancer DNA. Because cancer is an issue because it replicates very quickly, right? So if you break their DNA, they cannot replicate, and then they just stop growing. So usually you do surgery, remove your tumor, and then irradiate it, and destroy cancerous tissue, and essentially destroy its possibility of replicating. The most used systems are external ones. We call them teletherapy. If you go for the Greek, means therapy at a distance. Meaning we have a radiation source outside us, and the radiation will just get to the tumor. Originally they used cobalt-60 and cesium-137 sources, very strong sources, inside the steel and lead head. You had the source here, and you would point, very, very collimated source, you point it exactly to where you want. I just don't think you would be smiling like that in this case, but that's another issue, right? Now, essentially, they have changed these sources, because then you have very radioactive, strong radioactive sources, which may become an issue later. And now we use mainly things that we can switch on and off, like X-rays. You have very strong X-ray machines and high energy X-rays, which you can produce. There's ways to produce them, because then you can tune them, and those gamma sources, they are very penetrating, meaning they will get to the tumor and way beyond them. And not really what you want to, but then we use mainly X-rays now, because you can make them short, the path shorter, and then the range is shorter. They can just get to the tumor and not a lot more. Or you can do heavy ions, right, which is something else we'll talk about later. Many advantages, the big problem, price, cost. Or you can do internal radiotherapy, which is called brachytherapy, once again from the Greek, close therapy. In brachytherapy, essentially, you get a radioactive source of in some solid form, and you just put it inside your body, in touch with the tumor, so that the tumor will get the most of the dose, right? I'll show some examples of those things. And you see, in 1951, there was cobalt therapy, as they called it, or cobaltotherapy. It's using cobalt-60 source to, and it's interesting because this is a stamp, right, a postal stamp, and there was the decay scheme of cobalt-60 here. And they would use cobalt sources to irradiate tumors, right? As I said, we changed that for X-ray machines now. Brachytherapy, on the other hand, it's interesting because you introduce some wires or seeds straight, you put them in contact with the tumor, so then you can have a very high local dose and hopefully much lower dose to healthy tissue. You do that by choosing radioisotopes that emit radiation with a very short path, right? So the most used ones are iridium 192 wires, right, which are used to treat mammal head or neck tumors. You just implant a small piece of wire, something like a needle, right? You implant it close to the tumor and leave it there. Or you can use seeds of iodine 137. I'll talk about this in a bit, for prostate cancer, right? But and radioactive substances in this case are implanted in the desired region, sometimes after the surgical removal of the tumor, to avoid that new, just to sterilize and make sure there's no viable tumor cells that were left behind in some way. Or sometimes you use it to kill the tumor itself. You can, depending on the tumor, if it's small, you can kill it just by doing this without surgical removal, right? Let's just take an example, the iodine 125. It's very much used, and it's in the last stages of its development here in NEPAN 2, so that we can have it much cheaper than the imported ones. It's things the size of a grain of rice or something that you just essentially you sew them to your prostate, right? You put several of those, maybe 100 seeds or something. They are all bound to a small wire. It seems like a sewing thing, and you just put all of those around the prostate. The energy has very low radiation, so the effect in the rest of the body is negligible, really negligible. The person does a radiotherapy and has mostly no side effects at all. After 1 year, they cease to be radioactive because of the half-life, and essentially they keep there so the patient is hospitalized, you put it there, goes back home, and never has to returns hospital for routine tests to see if everything is okay. And if everything is really okay, you don't even need to remove those seeds, because iodine is not bad for you, and what you have but iodine is essentially silver and platinum, so no problem. And it has 85% efficacy seen. Okay, it's very, very good, and you don't have to remove the prostate, which I don't know if you've known people who have to do that. There are some people have very strong side effects from removing the prostate that can go from sexual impotence to urinary incontinence, for instance, right? So in therapy, the ones we use most, cobalt-60 and cesium-137, as I said, they were the first one we used. Now it's not that common to use them. We use phosphorus-32, strontium-90, yttrium-90. Usually these ones some of them we will inject in the body of a person in the form of some, we call them radiomedicine, because radiopharmaceuticals, that's the name, right? Because you bind one radioactive nucleus to a molecule that's for some reason will tend to concentrate on the tissue you want to destroy, right? Iodine, for instance, it's easy because iodine goes straight to the thyroid. So if you want to take the thyroid, take those to the thyroid, take radioactive iodine, and it's done. And now there's a lot of people thinking of radium-226, essentially not really radium-226, but one of its daughters, okay? And now we come to radiopharmaceuticals, which are used both in the diagnosis and maybe also for treatment, which is essentially, one thing is a radioisotope. A radioisotope is a nucleus, or if you want, an atom. Your body doesn't really know what to do with atoms. It knows what to do with molecules, with chemical components, right? So you have to get your radioactive atom and somehow implant it into a useful molecule, right? And then, depending on the molecule you use, you may use radiopharmaceuticals for cancer diagnosis, right? Mostly we have heard of it. Neurological and cardiac evaluations, because yes, you can do things that will show how, especially how glucose glucose, yeah, I think it is being consumed in your brain and in your heart and everything, right? And usually we have either gamma emitters like technetium, indium, thallium, iodine, or gallium, and these specific isotopes, right? Or the positron emitters, as I said, which are used for positron emission tomography. Like, just a few examples here. This is an image of a patient who took iodine 131, and you see that there's quite a big difference in iodine absorption between both thyroids. I'm no doctor, but I'm sure this means something, right? The most used in diagnostics are technetium, by far the most used one, hydrogen 3 or tritium, carbon 11 and oxygen 14, which are both for positron emission tomography. So they are on vogue now, but the whole system ends up being quite expensive. You have iron, cobalt, iodine. There's iodine 133 also, and so on. Just other things. There is an image of using 131. You see a thyroid and you see a lot of nodules. You shouldn't see that, right? So clearly this guy has a thyroid problem. This is another thing. They use gallium to check for addition. They already know the guy had cancer on the breast. Should be probably as a woman, because breast cancer can happen to men, right? It's not too much talked about. It's not that common, but it can happen. But I admit this is probably a woman. So the cancer in the breast and in the spleen was already known. They just decided to check if there was some other focuses in the rest of the body, and they could find in the abdomen and on the crotch. And these are not known before this exam, right? And then in the old days you would do like an x-ray, or something, you put some radioactive material in you and you have one sensor here, you have a 2D image, right? Bidimensional image. Then people started doing three-dimensional things, and then this has a name for it. And there's some problems here with names, because let's go first what tomography means. Tomography means reconstructing a three-dimensional image from two-dimensional projections. It's a mathematical term. And so there's two types of tomographies right now. First one you use a lot when you say, oh, I had to do a tomography in my knee or something. It's what they call transmission tomography, right? It's the CT scan, people say there. It's essentially a three-dimensional radiography, right? And another completely different thing is the SPECT, single photon emission computed. You see, it's CT, like the other one, computed tomography, but not transmission, but emission. This means you are the source of radiation. So in transmission tomography, you are just an absorber between a source, external source, and a detector on the other side. When we talk emission tomography, we're talking you are the source. So we put the source inside you, and one thing, essentially, yes, the radionuclide must decay, emitting photons, because that's what the detector will see, right? Most used for these ones are those we've already talked about, and essentially you go on doing you turn the detector around the person. Nowadays we use 3 or 4 detectors so that you only do a small turn and you have all the images. On the old days you would have to do like this and do the detector will turn 360 degrees around you. Nowadays they only do 90 degrees or something because you have 4 detectors, right? Or a bit more if you have 3. And well, then we come to another thing which is called positron emission tomography, as I told you before. The idea is you have a radionuclide that decays by beta plus, and if it decays, now you don't need gamma rays. If gamma rays are emitted, they will be ignored, because these beta plus particle will travel, and at some point it will lose all its energy and annihilate with an electron, right? And then you will have 2 500 kilo electron volt emissions, which are completely opposite one to each other, right? Why they are opposite? Because if the positron had almost no kinetic energy, it had almost no momentum. Electron also had no momentum. Momentum must be 0 again, right? And the only way for it to be 0 is that both are emitted on opposite ways, right? You usually have, there's lots of good things here. Most of these nucleus used for positron emission tomography have a very low half-life, minutes or something, meaning the time you leave the hospital you're not radioactive anymore. If you do, for instance, a scan using technetium, it's 6 hours half-life. You will be radioactive for some time. If you do something with iodine, you will be radioactive for some time too, right? These radionuclides, as they are beta plus decayers, they have to be produced in cyclotrons, and usually in a cyclotron inside the hospital, because the half-life is very low. That's why it gets to be quite expensive. But that's the idea. If you emit 2 gamma rays at the same time, right, you won't detect just one radiation. You will only say it's a valid event if you detect it in both places, in 2 detectors, and that reduces noise a lot. You essentially get your background noise to 0, meaning your image is much clearer. There's a down point. If you think the cell was here, that's where the decay happened, and this positron, it walked a bit inside your body, some centimeters, so the image is a bit blurrier, because this positron could have walked this way or this way or this way or this way, right? So you blur a bit your image by doing that, and that is what you end up. This is a positron emission system, and essentially this is, for instance, because you have very little noise, you can do very clear images despite the blur. And here, for instance, one of the things we can do, this is the brain of a normal person, and here's the brain of someone with Alzheimer's. So you see there's a place here with much more activity than on the normal brain, and on the other hand you see there's large parts here with no activity at all, right? And here, just a comparison for you, this is MRI, meaning magnetic resonance, nuclear magnetic resonance, right? Didn't talk about because it has very little to do with nuclear physics, right? Essentially, MRI shows you soft tissue in your body, right? It doesn't show other things, it shows where soft tissue is. So you see form, if you see, right? You see the form of your brain. Here is a PET scan, and here's SPECT. You see that PET scan has a lot more detail at some places, right? Although it may be, if you take a look here, a bit blurrier than here, right? Just because of the path the positrons walk before annihilating. But you see, you can see a lot of details that SPECT cannot, right? Here and here, I guess this becomes a lot clearer. Here too. So this is essentially what we have to say about these applications. But that's not all we have. There's something that was under development during the 70s and mostly the 80s. Small thing in the 90s. It has, nowadays it's just very small groups trying to develop it. It's boron neutron capture therapy. If you remember a charged particle, heavy charged particle like an alpha particle, it has a very, very short path inside solids, right? Microns. Which means essentially if you could make sure an alpha particle is emitted inside a cancer cell, it will destroy this cancer cell completely, obliterate it, and it would give almost no dose at all to the neighboring nuclei or cells. Sorry. Okay, so there's this reaction here I told you before. Lithium 7. You have boron 10 absorbs a neutron and produces lithium 7 and an alpha particle. The lithium particle also very short path. So if we could place some drug that's rich in boron inside the tumor and irradiate that in a neutron field, we would produce these alpha particles inside the cancer cells. And this would completely obliterate the cell without really giving too much dose to the next cell. The maximum range of these alpha particles is 9 millimeters, so very, very, very short. Okay? Now, it was common in the 70s, lots of research, but there's issues that have always kept it from becoming really operational. First of all is finding boron carriers that are selective for tumors. Because you want a boron carrier that will be in the tumor and not, because you will destroy completely the cell that has boron. So you must have almost no boron on healthy tissue. It's hard to do real-time dosimetry because you have an idea of how much neutrons are coming in, but it's completely different from what you do when doing another treatment, because in other treatments you have X-rays being emitted too, and you can follow up those. And the other thing is you need strong neutron fields. Usually this means nuclear reactors, and nuclear reactors, since Chernobyl, people have started to fear them quite more than they should, and so things started to go backwards. And then the truth is, some other thing came that could do most of what it does without including any of these problems, which is what we call hadron therapy or heavy charged particle therapy. So remember when we showed you interactions of heavy charged particles with matter, and I showed you that there was what I don't know if I told you the name. It was the Bragg peak. It deposits its energy mostly in a very short part of the path, and another thing, there's essentially no dose after that, right? Well, this is the Bragg curve for protons and for carbon ions, and compared here you have the gamma rays of cobalt and photons, 18 MeV photons from an accelerator, or 100 kilo electron volt X-rays. You see, you can deposit. It's much easier to concentrate the dose in a tumor this way, right? You just program your beam so that this dose will be delivered to the tumor. You have very little dose to the tissue before the tumor, and essentially no dose at all after the tumor. That's all you want, right? See here, for instance, if we do gamma rays, we aim the beam here to get the tumor here, and there's a lot of those after it. If you do higher energy photons, you can go farther, but then you have a lot of dose to the rest of the tissue. And with X-rays, it's hard to get deep. So it's perfect. It's excellent. The only thing is you require a high intensity proton accelerator or carbon accelerator. In fact, carbon is much more expensive, which means most of the facilities you find just accelerate protons. And here you have an idea. You know, every time you will do some treatment with beams, they had to do a simulation to what they call treatment plan, to see how much dose you will put somewhere. So here is a treatment plan thinking of 9 X-rays beams, because it's not one anymore. You do a lot of beams, because then you can distribute those doses, those side effects on different parts of your, let's say, brain or something. And then here you see, okay, we have the highest dose is on the tumor, which is the yellow line, but you have those on the whole rest of your brain in more or less dose. Especially if you think about here, we have the spine, and you see you wouldn't want too much dose on your spine, because there's sensitive tissue there. And here is what we do with protons. And now you see, look at this. We have a lot of dose in the tumor, the same thing we had there. Some dose on the entryway, but no dose at all to the rest of the body, including the medulla here, right? Spinal cord. Which means you can do three-dimensional energy. Well, chemotherapy, we all know, is just to take drugs that should tackle the tumor, but nothing to do with radioactivity. But it's usually very, very hard on the patient, right? And X-ray therapy is a bit better. Not really. There's no pain involved or everything, but the rest is bad. But when you think proton therapy, of course, this was made. This chart here borrowed from people who try to spread the word about hadron therapy. So take it with a pinch of salt if you want. You have three-dimensional energy distribution. You can do that with X-ray therapy. Okay, it just takes a lot of effort. This is something important, because you don't hit. You can plan your treatment so that you will never hit some tissues. So in this case, meaning the side effects are minor, and the impact on energy level of the patient, which is important, because if you think some cancer patients, they are really weak by the time they are doing their treatment. And so if you make them weaker, and chemotherapy does that, X-ray therapy to a lesser degree, but also does, if you can treat the patient without making him even weaker, it's much, much better for his recovery, right? So that's essentially proton therapy. It's a big thing now. Unfortunately, it's very expensive, so it's now only in a few countries. But these numbers are from a few years ago, but the total number of treated patients in the world is greater than 200,000, right? Only in 2014, just because this was the year I found, it's 15 in 1 year, 15,000. Most of them with protons, because it's cheaper, right? Carbon would be better, but it's too expensive, and sometimes it's better to treat 10 patients with a slightly worse equipment than treat one with decent. It's available as of today in 17 countries, essentially rich Europe, England, Austria, Czech, Denmark, France, Germany, Italy, and so on, and even Poland and Russia. Then United States and Canada, right? China, Japan, South Korea, Taiwan, Thailand, and Singapore, and now India too. And there's two in construction, one in Israel, one in Australia. Don't really know the stage, didn't have the time to check it this year. Should be, I believe, for next year or something. The idea is not new. The physics is well known for many years. In 1954, they did some tests in the United States, but because of laws there, Sweden started before them the clinical treatment of patients in 1957. United States could do that in 1961, Russia in 69, and England in 1989. It's an important thing. It was the first time they built one facility just for that. Okay, in the other cases they were using accelerators in research facilities to do that. In England, it was the first time they built a facility just for that kind of purpose. Now in the world, all these facilities I've put here are exclusively for this. In South Africa, they had in 1993, but they closed a few years later because it was a research facility that was adapted, and it was really hard to do both things at the same time. Yeah, you see, on the southern continent, there's nothing. There will be something in Australia, and in a few years, nothing in South America or Central America or Mexico or Africa, since South Africa closed it. So we need more and more of this, but it's expensive. Every year someone says something about building one facility like this in Brazil or in Argentina, but still have only heard words, not acts. Yeah? Let's get to see how good it can be. I have some examples. Some years ago we had the guy who ran Optis in the Paul Scherrer Institute in Switzerland can come here, and he gave us a nice speech, and I took some things from his speech. There's this Optis machine. It's exclusively for treatment of intraocular melanoma. So you have a melanoma inside your eye, and the only other treatment for this is the complete removal of the eyeball. So of course, if I remove your eyeball, that eye won't work anymore, right? And then over this 30 years working, because it's working since 1984, they treated over 7,000 patients. The healing index is really something to look at. 98% of the people whose tumor was still localized, meaning it didn't have metastases or anything, they could heal completely, right? And for small tumors, in 100% of the cases, you will conserve your eyesight. And if you have a large tumor, that decreases a bit to 90% compared to removing your eyeball, right? So you see the difference we have here. This is what proton therapy can do, and that's really something, but it's expensive. So that's essentially the main applications in health. Now, on the next classes, we will go on talking a bit about other applications, right? So keep tuned, a lot more to see.